Let's talk about the triangle. It seems so simple, right? But it's actually hiding a really powerful secret, a kind of geometric shortcut. And today, we're going to find it.
So, what is this secret? What's hiding inside every single triangle out there? Well, the answer isn't some complicated formula. No, it's actually a beautifully elegant piece of logic.
Okay, so take a look at a standard triangle, like this one here, ABC. Now, what if we find the exact middle of two of its sides? Let's call those points D and E. If we draw a line connecting them, that new line, DE, has this very specific, totally predictable relationship with the third side, BC. And you know what? That relationship is the key to everything we're talking about today.
Now, this secret actually has a name, of course. It's called the midpoint theorem. But don't think of it as some dusty old rule in a textbook. Think of it as the first amazing tool in our toolkit for today. Let's see what it can do.
And here it is. This is the core idea. The theorem basically says that the line connecting those midpoints does two incredible things. First, it's always perfectly parallel to the third side. Always. And second, its length is always exactly half the length of that third side. 2 for 1, every single time.
So, how do we know this is true? I mean, really know it. The proof is actually super clever. Instead of just measuring, it uses pure logic. You start by constructing a second, identical triangle right next to the first one. By proving those two little triangles are congruent, you can then prove that the larger shape they form, BCFD, is a parallelogram. And once you know it's a parallelogram, well, the properties of a parallelogram are what give us our two rules. The lines have to be parallel, and one is half the length of the other. It's just this beautiful, airtight chain of logic.
So let's just boil it all down to the absolute essentials. If you connect two midpoints in a triangle, the line you just made is going to be parallel to the third side and it's going to be half its length. That's it. That's the heart of the theorem.
Okay, so that's our first tool. Pretty cool, right? But what happens if we use it in reverse? If we flip the logic around, we get a second, equally powerful tool for our kit.
Let's try a different puzzle. What if you only know one midpoint? And let's say you start at that point and draw a line that's perfectly parallel to the base. Where's it going to hit the third side? I mean, could it be anywhere, or does it have to be somewhere specific?
Well, geometry has a definitive answer for us. It's called the converse of the midpoint theorem. And it says that your line is guaranteed to hit the third side at its exact midpoint. So if you start with one midpoint and a parallel line, you automatically find the second midpoint. It just works both ways. It's awesome. And this slide lays out the difference perfectly. With the original theorem on the left, you're given two midpoints, and from that you prove the line is parallel and half the length. But with the converse on the right, you're given one midpoint and a parallel line, and you use that to prove you found the second midpoint. They really are just two sides of the exact same coin. Okay, theory is great, but now it's time for the fun part. Let's put these tools to work. This is where it gets really interesting. We're going to use a simple rule about triangles to unlock the secrets of much more complex shapes.
All right, check out this classic problem. Take any random quadrilateral you can think of. Now, find the midpoint of all four sides and connect them. The question is, what shape is this new figure we just made, PQRS? The claim is that it's always a parallelogram no matter how weird the original shape was. How in the world could we prove that?
And here is the brilliant move. It's so simple. You just draw a diagonal, and boom! Suddenly that complex quadrilateral is gone. What we have now are two simple triangle problems. We just turned a shape we don't have a rule for into two shapes that we absolutely do.
Okay, so let's follow the logic. In that top triangle ABD, our theorem tells us that the line PS is parallel to the diagonal BD and it's half its length. Got it. Now look at the bottom triangle BCD. The theorem tells us that QR is also parallel to BD and also half its length. So wait a second. If PS and QR are both parallel to the same line and they are both equal to the same length, well then they have to be parallel and equal to each other. And any four-sided shape with one pair of opposite sides that are both parallel and equal is, by definition, a parallelogram. And just like that, problem solved.
So think about what we just did. A simple rule for triangles helped us crack a complex problem about quadrilaterals. But it goes even deeper than that. The midpoint theorem isn't just some standalone trick. It's actually part of a whole family of theorems about parallel lines and proportions.
So, meet the equal intercept theorem. This is like the midpoint theorem's bigger, more powerful cousin. It takes the same core idea, but just expands it from a single triangle to basically any system of parallel lines. So here's the principle. If you have a bunch of parallel lines and one line crosses them at equally spaced intervals, then any other line that crosses them, no matter the angle, will also be cut into equally spaced intervals. See how our little triangle rule is just a special case of this much broader idea? It's all connected.
So we started with a simple triangle and found a key, the midpoint. That one little key unlocked a powerful theorem, its converse, and even a way to solve problems with way more complex shapes. Which really makes you wonder, right? How many other simple keys like this are hiding in plain sight, just waiting for us to find them and unlock the rest of geometry?